that, accept that. Okay. So here's what we're doing today. I'll review that Gizmo lab real quick and show you how we actually are going to use the big 6 problems today to plug into the F equals M times A. So we'll finish the last part of the Newton's laws lecture, and then you'll have problems again, just like we've been doing the last Friday and Monday. And then hopefully another lab on Friday, another online lab, obviously, before we start reviewing for the test. What we're hoping is that, and we'll see if it changes, again, we're planning on being back next Thursday with cohort A. So we're hoping that we can do the quiz or the test in person instead of having to do that on a Google form. But we'll see what the health department says between now and then. Okay, so today we're gonna, you guys should be able to correctly solve F equals MA, but substituting acceleration with the acceleration formula, and then solve for V and D from those big 6. So final velocity and the distance traveled. And that sets us up with a little review of the gizmo. So here is the gizmo from the other day. And if we just put one fan on and turn it on and then play it. And then what I like about this, and you guys did a pretty good job going through it. If you weren't getting it, don't forget, you can still ask for help on Tuesdays and Thursdays when I'm here, or ask for help while we're doing the lesson. But here's what I like about this is that it graphed everything out. Here's the acceleration graph. Okay, it's accelerating at a constant acceleration. And for this one, I'll show you what that is in the table. Here is the velocity graph. So you have that constant velocity that increases by whatever the acceleration is per second. And then you have the distance over time graph, or the distance traveled up to 10 meters. And you can see the distance traveled, they get there quicker once it accelerates more. Now watch what happens if we add another fan to this distance, how quick it gets there. Switch her around. So you can see it got to the 10 meters quicker or in less time. It only took 4.3 seconds here, whereas 5 seconds, I believe, with only one fan. Okay, so here's what I want to show you. I'm going to move my camera real quick. So if you look at this table again, God darn it, let me reset it. If you look at the table, it'll show you the numbers here. So acceleration is 0.80 meters per second squared. The final velocity, the VF, is 4.0 meters per second. And the distance traveled was 10 meters. Now look at this now once I share my camera. Okay. Now watch this when I share my camera. See if this is... Okay, now listen, you might have to pin my screen to see this a little better. But here is the big 6. Here's the big 6. And if we're solving for distance, the initial velocity was 0. So this can just cancel out because anything times 0 is 0. So we're really taking 1/2 times the acceleration times t squared. Now remember, the acceleration was 0.80 meters per second. The time was over 5 seconds. So if we do the math there using the big 6 for distance or displacement, we get a displacement of 10 meters. And that's how far that car traveled. So the nice thing about the gizmo is it does all that for you, but this is actually using the formula to solve for that. You can also solve for final velocity. Here's final velocity. Remember, V naught was 0. So it's just acceleration times time. Your acceleration was 0.80 times a time of 5 seconds. So your final velocity, just like the gizmo told us, was 4 meters per second. You can solve for acceleration a couple of ways. Okay, starting with this one over here, the original acceleration formula, Vf minus V naught over T. Vf was 4 meters per second minus 0 divided by a time of 5 gives us an acceleration of 0.8 meters per second squared. Or you can use Newton's law, second law, F equals ma, so A equals force divided by mass. The force of each fan is 4 newtons. It tells you that in the gizmo. Each fan weighs 2.5 kilograms, and the cart by itself was 2.5 kilograms. So it'd be 4 newtons divided by 5 kilograms, or 0.8 meters per second squared. So that's the math that we've already been doing in taking the data from the data table. I'll show you that again. Taking the data from this data table right here, where we have acceleration of 0.8, a final velocity of 4, and a distance of 10 with a time of 5 seconds. So plugging all of those in using the kinematics formulas gives us the answers that this table gives us. So I thought that was pretty good. Okay. Take out, you should have your PowerPoint lecture notes. What the zoom in's going on. You should have your PowerPoint lecture notes. So the packet, we're going to finish these up and also have a calculator with you. Also have a calculator. Okay, so here's what we're going to do today. Going back to the agenda and the learning target, you are going to use the F equals ma still, Newton's second law, but substitute acceleration and also be able to solve for V and D once we get these different answers from the F equals ma. And then how do we connect this to the prior lessons? You guys have already learned the big six. We've talked about Newton's law, and you've also been using F equals ma. So it should all come together nicely. All right, so here's the lecture right here.
Fans, do you know that from the start of the year we have been working on the same problem? Today we take one more step in that direction. By the end of class today, you will be able to apply the second law and the big six equations of kinematics to problems utilizing algebra to enhance problem solving. I know, algebra, I hate algebra. Well, life's a word problem. You just can't get away from the mathematics. So Newton's second law, deceptively simple, F equals ma. By the time we're done, these will be the hardest problems of the year. We keep adding to them step by step. So it's important that you take each of these small steps so the problems don't overwhelm you. Let's now take Newton's second law and add kinematics in the big six. You remember the big six equations for kinematics.
Okay, so listen, I'm going pretty fast, which is okay because we've already had a lot of these slides before where F equals ma. All of the kinematics problems are up here. You worked with these before. Don't be scared because they have a lot of different things in parentheses and all that stuff. You know how to do it. You know how to plug it into a calculator. So we'll probably just we'll get into the problems and start practicing a little quicker today so you have more time to work on the problems and ask me questions if you have them.
We've used these in the last chapter. We'll be applying those now to what we have with Newton's law? Well, we started with given mass and an acceleration, and we're told to find the applied force. No problem. F is ma. Now, on our next step, we added algebra to this. You were given a force and a mass, but no given acceleration. How do you solve Newton's second law for acceleration? Well, F is ma, easy enough to get mass from one side to the other. Acceleration is now force divided by the mass.
And just remember what we talked about earlier this year too. If you want to get one of these givens alone, you do the opposite of what the other given's already doing. Mass is multiplying times acceleration. So we divide each side by mass to cancel out. And that's how we get the A equals F divided by M, because we wanted to get A alone, which we did. So we can solve for acceleration using this formula here also. If we know the force, like we did with the fans on the cart, and we know the mass, like we did with the fans and the cart, we can solve for acceleration.
And now what? Kinematics. Newton's second law, easily algebraically manipulated to solve for acceleration, and then use that acceleration in the big six equations of kinematics. Well, how will it work? Well, what if
Okay, so listen, here's a little snapshot of what we're going to do today. Once you solve for acceleration, force divided by mass, you can now use that answer to solve for final velocity or displacement, depending on what givens you have. Just like we did before with the big six, we had to list our givens to determine which formula to use. But we'll take this acceleration and we can plug it into here. Notice there are 1, 2, 3, 4 of these that have acceleration in the formula.
Well, what if we are given a force, a mass, an initial velocity, and a time, and told to solve for final velocity? A daunting task from the looks at it, but break it into simpler, easier.
Okay, and here's why I like this, how Coach Roop set this up, because yes, we have a lot of givens here, but what we do on the problems, it will say solve for the acceleration first, and you can solve for the acceleration using these two givens here. Acceleration equals force divided by mass, and then the problem might say, what's the final velocity, or what's the displacement, or what's the time? And you can plug in that acceleration to solve for these givens. So I think you'll get it once you practice them.
Easier to handle steps. First, start with Newton's second law. Well, we know that Newton's second law says F equals ma, and it's easy enough to algebraically manipulate this for acceleration. So A is F over m. Now that I have my acceleration, now what? Now look at the kinematics. Look at the kinematics equations. One of these has final velocity if I know initial velocity, acceleration, and time. Which one? And there it is. So with the givens that I have, with 2 steps and a little algebra, I can find what my future velocity will be. Let's look at another. What if we are given the force, the mass, the initial velocity, and the time? This time told to find displacement. Well, it's easier in smaller steps. First, start with Newton's second law, F is ma. And with a little algebra, I have my acceleration. Now what? Well, now kinematics. One of these equations has displacement if I know initial velocity, acceleration, and time. Which one? Right there, the displacement equation. So with these givens, I can solve for how far I will be at some future point. How about if instead we are given the force, the mass, the initial velocity, and the displacement, no time, and told to find the final velocity? Well, again, start with Newton's second law. F is ma, and with a little easy algebra, I can determine the acceleration. And now what? The kinematics. Notice with this one, I don't have time anywhere as a given. Well, when I look at my big six equation for kinematics, only one of those does not have time as a variable. Makes this one an easy choice, the v squared equation. So with these givens and what I'm looking for, I would need, first of all, Newton's second law, then the v squared equation solved for final velocity. Now, lastly, what if we are given a force, a mass, and final velocity and time, and told to find the displacement? Well, again, it's easier to do it in small steps. So I grab Newton's second law, F is ma, and it's easy to do just a little bit of algebra, and I have the acceleration. And now what? The kinematics. Only one of the big six equations has displacement if I know final velocity, acceleration, and time. And there it is. So with these givens and what we're looking for, I would use the final velocity form of the displacement equation. Well, let's take it out for a test spin and see what happens. Whenever I have a physics problem, the first thing I have to do is, indeed, a 1964.5 Ford Mustang. True story. Ford wanted to make sure they got ahead of the pack, so they brought out a new car in March rather than September, and that was the 64.5 Mustang. They were fun cars. Europe had had fun little cars for decades. And Chevy, of course, had the Corvette. Ford wanted into this, but they wanted something that everybody could drive. It came with three models: the convertible, the hardtop, or the fastback, racing stripes, and a fun little interior. Bucket seats so that each passenger in the front had their own individual seat, and a 4-speed manual transmission on the floor attached to, well, usually a 4.9 liter, 289 cubic inch, two barrel Ford V8. Now, it was a fun little motor, but it wasn't the real muscle people wanted. Well, within 2 years, you would be able to order, instead of the 289, the Shelby Cobra Le Mans 7-liter, 427 cubic inch V8 racing motor with two 4-barrel carburetors. So each of those cylinders in that V8 motor had a targeted carburetor port acting on it, and that would move them around. Within a couple years, Shelby brought out their own model, came with multi-port fuel injection. And either one of those 7-liter motors with two 4-barrel carburetors or multi-port fuel injection, either one would smoke them off in all 4 gears. Not only that, in the hands of somebody who knew what they were doing, it would pick them up and move you down the road in a hurry. So those Mustangs, a 64.5 Ford Mustang with a mass of 800 kilograms starts at an initial velocity of 15 meters per second and is accelerated by a force of 5,250 newtons. Determine the car's acceleration and the final velocity of the car after 5 seconds.
Okay, so using your calculator, you guys start with determining the acceleration. You know the force and the mass. So the force is right here, 5250. Divide it by the mass. That will give you the acceleration. And then, if you feel comfortable, see if you can find the final velocity from the big six, or just try to determine which formula you'll use from the big six to determine the final velocity. So again, the first thing we're doing, and this seems like a pattern that we'll probably do this for all of the problems, is finding the car's acceleration, and that's just force divided by mass. So if you plug that into a calculator, force divided by mass, you get an acceleration that starts with 6 something. And then you'll use the big 6 for your final velocity. Now remember the givens they give us. Initial velocity and acceleration. And it doesn't look like we have the time in this one.
Read it. After I read it, and there's that Ford Mustang with a fast back. It's an 800 kilogram mass and starts at 15 meters per second. They apply a force of 5,250 newtons for 5 seconds. Read it, diagram it. After I diagram it, now right, my mass at 800 kilograms, my initial velocity.
I misspoke on that. It does have a time of 5 seconds. So now once you look at this, let's put the givens up.
15 meters per second. A force of 5,250 newtons is applied for 5 seconds. Determine the acceleration and the final velocity.
So again, you'll start with determining the acceleration. Force divided by mass divided by, or force divided by mass. And then once you get that acceleration, you'll use one of the big 6 that includes initial velocity, time, and acceleration.
Well, it's daunting if I try to do it all at once, but if I break it down into little parts, it's easier to handle. First, we need to find the acceleration. Well, Newton's second law, deceptively simple, says F equals ma. And with a little algebra, the acceleration is the force divided by the mass. Read it, diagrammed it, in the givens, no one looking for. Pick my equation, did the algebra. Plug and chug. What do you get? Correctamundo, 6.56 meters per second squared. Well, now I have my acceleration. What will be my final velocity after 5 seconds? Well, here I need the big 6. And one of those will tell me final velocity if I know initial velocity, acceleration, and time. No algebra necessary. Plug and chug. Parentheses are important.
So actually try this on a calculator right now, because just like before, a lot of times the most difficult part is plugging it into a calculator. So type this in and see if you get the answer that we come up with.
What do I get? .8 meters per second. Yeah, from 15 meters per second, 30 miles per hour. With that Ford Mustang and standing on it, you could get yourself up over 100 miles an hour in 5 seconds. They would move. But people who know cars that move don't grab Ford Mustangs.
Okay, so listen,